Okay, good morning, guys. It's 9 a.m. and we can start. First of all, a few announcements. First one, I sent you email about the quiz, right? Quiz number 4. It's simple, but in the previous couple of semesters ago, I noticed that once I give a question on the exam about finding the equivalent resistance between different points, lots of students struggle with that. I was quite surprised, so as a result, that was the goal of this quiz, right? To force you to think about this in advance and realize that you can find equivalent resistance between any points, 2 points, right? Whatever the goal is in the problem. So quiz number 4 is due Wednesday midnight, right? It's very simple. It shouldn't take much time. And again, submit it to the grade scope. Then today, no office hours, right? Usually from 2 to 3, I have office hours, right? Sometimes students come, sometimes not. All right, so today no, because we have PhD qualifier exam and I must be there. Then our chairman, right, they created midterm evaluations, and he keeps asking me to remind you about that evaluations, right? I sent you the links, right? If you have time and whenever you have time, you can go and leave your sort of midterm evaluation. So just department wants to know. Right? But of course, at the end of the semester, there will be the final evaluation. So these are announcements, and now let's move with our material. So today, we need to discuss power, and only then only then RC circuit. But we haven't finished the example from the previous lecture, right? You remember we introduced Kirchhoff rules, which can be used to analyze any circuits, no restrictions, right? It doesn't matter if resistors are connected in series or in parallel, or they are not connected in series or in parallel, right? Universal rules, right? So let's finish that example. And then we will start discussing power and RC circuits. Okay, let me switch to the whiteboard. And almost there.
I don't know why you mentioned
somebody's mic is on. All right. Okay, so you remember. We started discussing this example where I put lots of magnets so that it wouldn't be erased. Of course, this example was over here, but I moved. So we had this circuit, multi-loop circuit, remember? And we need to analyze it. Basically, we need to find all currents. And once you know the currents, of course, you can find potential differences across any of these elements, right? So 3 unknowns, and we've made a few preliminary steps before we started writing down the equation. So first, we identified junction points, because every time we're dancing around those points, A and B. Then we introduced currents, because between junction points, a current is the same, right? In this branch, and that branch. So 3 currents we introduced, right? Direction of the current, don't sweat, don't think. It's difficult to predict. I mean, to guess the right direction. So just pick any direction, this way or that way, it doesn't matter, as I explained to you in the previous class, right? At the end, you can adjust it. So we picked I1 this way, I2 is here in this small bridge, and I3 is over there, right? So I picked this direction. Again, nothing wrong if you pick this direction. Okay, and then the last preliminary steps, we choose a travel direction. Travel directions are very important, so that we'll know which points are final and which points are initial when you calculate potential differences across each element, right? So these are 3 preliminary steps, and then after that we started writing started applying our rules. First we apply junction rule. The total amount of currents entering must be equal to the total amount of current leaving a junction point. Okay, so we wrote down for point A junction rule. So we have 2 currents entering I2 and I3, and 1 current I1 leaves, right? So we have this equation. Then for B, I1 enters, I2 and I3 leaves. So we wrote this down. Obviously, this equation and that equation are identical, right? In fancy words, we can say they're linearly dependent, right? So, but anyway, it just basically means the second equation doesn't give us any additional information. We can just trash it, right? So it's redundant. So, and it's not by accident. Every time if you have a circuit with n junction points, there will be only n minus 1 useful junction equations. Every time one junction point is not going to give you a useful equation, right? Okay, so it's the first equation useful, right? And of course we need 3 equations because we have 3 unknowns, I1, I2, and I3. So we need to introduce 2 more equations. And of course they must come from loop rule, right? So loop, let's write it for the loop number 1, right? So loop 1. So the first equation, oh, actually it will be the second, but the first from the loop rule, using loop rule. Okay, we have all the steps on the picture, right? I mean, all the information. So now we need to pick a starting point. Again, it doesn't matter where you start. If you start at a different point, just the order of terms in the equations in the equation will be different. But who cares about the order of terms? Right? So I will start over here at this point. So let me write. So that's my starting point. Why that point? Because I have this minor compulsion. I like when there is an EMF at the beginning of the equation. It's just for me, it looks nice, right? That's the only reason. Every time I'm trying to cross the battery first. Right? So in this case, if I start over here, so first I need to cross this battery with EMF, with the EMF 1, right? Okay, now you have all those rules which we developed in the previous class. I just remember them. I didn't want to write them here, lack of space. So whenever you cross the battery from minus to plus, rule number 1, contribution to the equation is plus EMF, right? So over here, I will just write plus EMF, of course, 1. So that's contribution to the loop equation from this battery. Now after this, we're up against this resistor with resistance R1. Okay, so travel direction, you see, down. Current direction also down. So directions are the same. Rule number 3, if directions are the same, if you're dealing with the resistor, contribution to the loop equation is negative, and the value of that contribution, IR. In this case, current I1, resistor R1. So minus I1 R1. So minus I1 R1. Then, so we pass this. Now we have to go here, and now we have to go up through this small bridge, right? So now we're up against this resistor R2. So let's look at the directions. Current current now is I2. So current is up, travel is also up, the same directions, travel and current. Again, the same rule number 3, which you have in your notes, right? So contribution will be negative, minus I R2. And here on purpose, I didn't write now the subscript in order to emphasize, very common place for mistakes, right? Very often here there are few elements, right? And students develop a habit of using current I1. And when they come over here to this part of the loop, but here current is I2, but they still keep writing the same I1. Very often I see that mistake. Very silly. Of course, when they see that it's, when they realize that how silly that was, of course they come out somewhat not happy students. Right? So be careful with these subscripts. Pay attention. Right? Of course, it's just a lack of attention. So here it's a I2, R2. Right. Okay, so now, and minus, because directions are the same. And now after this, we're back to the starting point. So we completed the loop, and now we need to complete the equation. We need to complete the equation, so it must be equal to 0. Don't leave in this form, because very often, actually, lots of students on the final exam, on the second midterm exam, they just write bunch of these terms without writing that it is equal to 0. It's not an equation in that case. It's just a bunch of terms you collect. You need to write an equation. Of course, usually, if I grade, I subtract a few points, right, for not writing the equation. Come on, we're not, you are science majors, right? You're not from, I don't know, nutrition department or whatever, right? Philosophy department, right? If it's an equation, it must be an equation, right? Okay, so that's the equation number 2, right? Let me check if I didn't make any, no, everything is good, of course. So that's equation number 2. And now the last equation must come from the loop number 2, from this loop. Again, you can start from any point. You remember my compulsion, right? So I will start from this point. So this will be my starting point. And travel direction counterclockwise. So again, I am up against the battery first, so that I will have EMF in front. So again, we travel from plus to minus. So it means that, again, rule number 1 in your notes. So it means the contribution will be positive. Plus, and now, of course, EMF 2, plus EMF 2. You see, it's very mechanical. Once you solve a few problems, 2 problems like this, writing down these equations is like this, right? It's very mechanical, very straightforward. But of course, you need to practice those rules. So now, after this battery, you have to cross this resistor in this loop, right? So now, travel direction in the loop 2, down. Right, travel direction is down, but current I2 is up. So now directions are opposite, right? Directions are opposite. Current is up, travel is down. So contribution, it's a rule number 4 in your notes. So contribution must be positive and product of I and current and resistance. So it will be plus I2 R2. Okay, so now after that, there is nothing, and now we have this resistor in front of us, R3. Again, let's look at the directions. And again, when you deal with battery doesn't care about your current directions. To analyze a battery, you just need to know only the travel direction. But when you deal with resistor, both directions are important, travel and current. Because again, sometimes in the past, students were confused, right, about this. So now, travel is up, current also up, directions are the same, right? So it means contribution must be negative. Rule number 3. So it will be minus current I3, resistor R3. And again, so now we're back to the same point. Don't leave your answer in this form. Again, it's just a collection of terms. It's not an equation. So it must be equal to 0. Because without equals to 0, it looks like a beheaded equation. So 0. Right. Okay, so now this is our equation number 3. So what now? 3 equations, 1, 2, 3, 3 unknowns, physics is over. Now it's just a math. Okay, it's just basically, I want to say calculus, no, it's algebra. It's algebra, solving 3 algebraic equations with 3 unknowns, right? Of course, if you try to do it on paper, it would take you maybe 15, 20 minutes, and still, I wouldn't guarantee that if I try to do, still possible to make some mistakes, right? Algebraic somewhere, right? Or you can just use your calculator, enter coefficients, right? And your calculator can give you answers. Right? I didn't know. Students showed it to me. That's very fast. Okay, of course you can say, come on, but there is another loop. There is a loop number 3, this external one. You can pick this loop, for example, right? But there is no need in that loop, right? Even if you write the equation for that loop, you can look in my notes, right? I will post a PDF file, right? So I wrote down this equation, that equation. If you write it down, you will see that that equation is basically superposition of these two equations. What does it mean? If you add this equation and that equation, you will end up with the equation for the external loop. It means that equation is a linear superposition of linear combination, can be written as a linear combination of these two. It means that it doesn't give us any additional useless or useful information. Right? So in this case, this loop and that loop is enough. External loop, yeah, you can write that equation, but again, there is no need in that. It doesn't give us any additional information. Okay, so, and again, so once you solve it for currents, if your current, for example, let's say I1 at the end will be negative, let's say minus 5 amps, what it means? It means that you know the value of the current, 5 amps, and minus would just indicate that my assumption about current direction, I1, is wrong. So it would mean that current actually flows from this point to that point, right? But if current is positive, okay, it means that you are good at guessing, or I am good at guessing. Okay, so as I said, if a problem like this is given, it shouldn't take more than a few minutes to write down these equations. Right? Usually I don't ask for solutions, right, for currents, because it would take plenty of efforts just in terms of algebra. Okay, so that's the example. It should be enough. We looked at one example in our recitation classes, and now let me switch back to the presentation in order to start discussing electric power. All right, code is over there. Now I use different colors, so now it's visible both on the blackboard, on the whiteboard, and on the green screen. Switch. Okay, we're back. And I like this picture. Garfield's cute. And plus, yeah, soon is going to be Halloween, right? I don't know exactly, but soon. So, electric power. And let's sort of ask ourselves conceptually philosophical question. What a term, right? Why do we use electric energy? What's so special about this? Why not, for example, thermal energy? It's also good. Why we're discriminating thermal energy, right? Of course, the answer is more or less obvious, right? Because yeah, thermal energy you can also, for example, transport from over short distances. For example, from the basement where the boiler is to your house, right, warming the house. But it can be done only over short distances. But electric power, especially AC, right, electric energy, can be transported over thousands of kilometers, right? Again, especially when we switched from DC to AC, right, at the beginning of the 20th century, right? So now when we use AC current, right, so it can be transported over long distances with small losses, right? So the first reason why we use electric energy, because it's easier to transport over long distances. Then second, okay, let's say now the electric power, okay, electric energy is delivered to our house. And how do we use it? How do we use it? Do we use electric energy directly? For example, let's say, how do we use it? Let's say I feel like chilly, right, in my apartment, right? So what do I do in this case? I would take a heater, plug it in the outlet, right? And what does that heater do for me? It transforms electric form of energy from the outlet into heat, thermal energy, right? Because that's what I want. So pretty much this heater works as a transformer of one form of energy into another forms of energy which I want. Then, yeah, for example, here, or fan, electric, right? Electric fan. Then let's say I want to, I don't know, vacuum my floor. What do? All right, I would grab my vacuum cleaner, right? Again, plug it in, and what happens, right? So this vacuum cleaner transforms electric form of energy into first mechanical, and then that mechanical, right, it can create sucking, right, and it sucks the dust, right? Again, what does it do for me? It transforms electric form of energy, in this case, into mechanical form of energy, right? Then let's say I want light, right? So what, I take a bulb, plug it into the outlet, and again, bulb transforms electric form of energy into light. Then let's say I want to generate electromagnetic waves, like take a router, right? And again, plug it in, and it will generate electromagnetic waves, right? So every time you see, we transform electric form of energy into other forms of energy. Pretty much all these electrical devices which we have in our houses are basically transformers, right? Of electric form of energy into something else. You know what? At some point I started thinking, so where do we use actually electric form of energy directly without transforming it into something else? And of course, yeah, the reason why we use electric energy, because it's easier to transform this form of energy into any other forms of energy. Try to transform, for example, thermal form of energy into light. Yeah, or mechanical. Yeah, it's possible, right? But it will be ridiculously complicated, right? So it's easier to transform. Right? Okay, back to direct application of the electric form of energy. And after thinking for some time, I couldn't come up with more than 2 examples. If you can think of something else, let me know, right? I can think of only 2. Let's say a person has a problem with the heart. So in order to start it, doctors or nurses use that device, right? Not very pleasant examples. Actually, the second one is even worse. Of direct application of electric form of energy. Electric chair, right? These are only 2 examples, horrible examples I can think of, right? Otherwise, all the time we transform electric form of energy into something else. Okay, so now the next logical question. If we transform all the time electric form of energy into something else, of course the logical question, how much of energy do we transform? Right? Absolutely logical, right? So if first it's in electric form, then mechanical, for example, so how much? But actually, researchers, scientists, right, went even one step deeper in this question. They don't ask just how much of energy is transformed. They ask how much of energy per unit time is transformed. What is that? Amount of energy per unit time? It's power, right? Electric power. So that's how we naturally come to the idea that we need to introduce electric power, because all our devices are basically transformers. Transform one form of energy into electric form of energy into other forms of energy. Okay, so now next slide is about the actual formula, right? Okay, once or twice I derived this and then I stopped deriving it, right? So it's a formula for the electric power. For example, you can, let's say you have some device, right? Maybe it's just a resistor, the simplest case, right? So potential difference across the resistor, delta V, current flows through the resistor, right? And this very simple derivation, it leads that amount of the power, of course, in this case, what electric form of energy is transformed into thermal, into heat. So this resistor, for example, gets warmer, right? So how can we calculate power? Yeah, here the short derivation, right? It's just the product of potential difference across the device, across the element, n times the current flowing through this element. It looks like Ohm's law, but in Ohm's law we divided delta V by I, but here we multiply delta V times I. Right? So this is the power dissipated in this resistor. Okay, so yeah, you can use a formula in this form, but sometimes it depends what is given in the problem, right, and what is given in the problem. Sometimes it's more convenient to write it in terms of, for example, potential difference and resistance, or current and resistance. And of course, we can easily rewrite in those forms using Ohm's law. Right? So if this is the original form, and then if you use Ohm's law, you can write it in terms of delta V and R, it will be delta V squared divided by R. In terms of current, it will be I squared times R, right? Just trivial transformations, right? So you will get these two forms of this equation, right? Again, sometimes it's just easier to use this or easier to use that. We will discuss that. We will look at the examples. Okay, so that's how we naturally comes to the idea of electric power and why we need it, right? And now I think it's time for that question. Yeah. Okay, in your chat, I created the poll, the first one, conceptual test 1. So what do we have here? We have two bulbs. One is 60 watt, the second is 120 watts. Okay, I don't have 120 watts, I have just two 60 watt bulbs, right? And they're connected like this. Right. And obviously, you see they are connected in series. And they're driven with this battery, delta V. It can be anything delta V, right? Nothing specific. But it's strong enough to make these bulbs glow. Right? Okay, the question is, which bulb generates more light? 60 watt or 120 watts? I like this question. It's not completely trivial, right? So you need to know one important piece of information, which actually, frankly speaking, I didn't know before I started teaching. Right? Actually, a few years ago, Dr. Mittler actually suggested, you see, there's an interesting question, right? So we can use it. And I looked and, yeah, I like it. And I started using this question. Okay, so give it a try, all right? Do your best, and then I will discuss. It will take probably, I don't know, 5 minutes, right? There will be a somewhat long discussion. Right? Okay, so again, the poll is in the chat. You can see it. Yeah, I can see it. It's in front of me, right? And after like a minute, I will start discussing this. So which bulb is brighter? A or B or equal? They have equal brightness. Right, let me scroll slightly up so I can see your answers. Okay, yeah. 62% for A, 12% for B. Something it will be equal. Yeah, you still answering? Cool. Still answer A is the leader in our election. All right, 61, 20, 18. Okay, I think it should be enough for you to start thinking, right? And now let's discuss that. So, first of all, we need to understand what does 60 watt mean in this case. In order to do that, we need to realize, so how do we use, okay, actually not realize, right? We all know how we use the bulbs, right? So we just, in order to use the bulb, we just grab it, right? Put it in the lamp and plug it in the outlet. And how much of potential difference do we have in the outlet? Of course, 120 volts, right? And of course, the companies which builds these bulbs, of course, they also know that. Of course, for example, here I have this company, right? So yeah, it's in Cleveland, but still made in Hungary. But of course, made for the U.S. market, right? So these bulbs, right? I have this box. Right? So of course, the people who build bulbs, they know that we are going to use, people in the U.S. are going to use these bulbs, plugging them into the outlet with 120 volts potential difference. So every time that's by default, we use them with 120 volts potential difference. Of course, they calculate, but they calculate the wattage, assuming that we use 120 volts. So all these numbers, these wattages, right, 60 watt, 120 volts, calculated assuming that we use potential difference of 120 volts. So basically, in US, these numbers, right, 60 and 120, it's like an intrinsic property of these bulbs, but only in the US. If, for example, I grab this bulb and go to Europe, for example, to Ukraine, right, visit my friends, right, these numbers would mean nothing, because their potential difference in the outlets is 220 volts. If you go to Africa, maybe the potential difference over there is different. I don't know. And of course, these numbers will be completely useless. Okay, not completely, but close to that. So you see, these numbers are useful only if you live in the US or in the country which also uses 120 volts potential difference, right? And in our example, we don't have 120 volts. So these numbers for this example are close to being useless. So we need to replay this game completely. So now we need to come up or get some information about some true intrinsic parameter of the bulb. So what can that be? True intrinsic parameter. It means that it doesn't matter where you use your bulb, that parameter will be exactly the same. And I think about the resistance, right? Resistance of, for example, this bulb or resistance of that bulb. It doesn't matter where you use it, in the US, in Africa, on the moon, it doesn't matter. The resistance is going to be the same, right? So let's find information about the resistances of these bulbs in order to get information about the actual power produced by this bulb and that bulb. Because these 60 watt and 120 volts, they are not truly intrinsic parameters. Again, they're intrinsic only for the territory of US, right? So, but of course, we need to use these numbers in order to get information about that resistance, right? So we need to use the formula which we just derived, right? Presented formula for the power. And which formula I want to use? It's better to use, right? We have three, right? I times delta V squared over R, and I squared times R. We know that these numbers were calculated assuming that delta V is 120 volts. So we know delta V. I want to get information about R resistance. and power is given, right? So it's better to use, okay, I didn't press on the slides. It's better to use this formula, right? Delta V squared over R. Because again, as I said, delta V is 120 volts for this 60 watt. And I want to get information about resistance over 60 watt bulb, right? So it's better to use this formula, right? And of course, 120 volts divided by R of 60 watt battery. So, well, not battery, bulb, all right? So where I can solve it for R of this bulb, right? So it will be 120 squared divided by this 60. So as a result, of course, you can actually calculate. I didn't, because we just want to compare which one is brighter at the end. So that's what I get. That's how I can get information about the true intrinsic parameter of the bulb. Right. Again, as I said, you can calculate. Let's do the same for 120 watt bulb in exactly the same way. So the same formula. So power is given. And of course, this power is calculated assuming that 120 volts is used. Of course, we can get resistance for the second bulb. Again, you can calculate number. I didn't. So now we can compare which resistance is larger. Of course, since numerator the same, denominator is smaller in this case, so of course resistance over 60 watt bulb is larger. Okay, now once we know information about this intrinsic parameter resistance, now we should be able to calculate the actual true power for this case. And which formula should we use? Again, now we need to use those formulas for powers, right? I times delta V squared over R, or I squared times R. We have information about the resistance, and current is the same flowing through these bulbs because they're connected in series, right? So it seems like formula I squared times R will be the best, the easiest. Of course, you can use any of those formulas, but if you use other formulas, right, you will have to make 2 steps instead of 1 step. So why would we want to make 2 steps, right? Of course, it's better to use I squared times R. And I will add now, it's a power actual for this case, right? Here, we just use information which is written on the box, right? In order to get information about that intrinsic parameter. And now we can get true power for this situation, which we have in this circuit. Right? Okay, so that's what we can write for the actual power over 60 watt bulb. And very similar we can write for the second bulb, right? I squared times R. So now we can easily compare these powers, right? Currents are the same, because these 2 bulbs are connected in series. And we have information about the resistances. So R60 is larger than R of 120. So it means that power over 60 watt bulb is larger than the power produced by 120 watt bulb. Right? So you see, this answer is not intuitive at all, right? In the previous class, some students, like 8, I noticed, right, they answered this question, right? I don't know why. And they all picked, of course, 120 watt, right? But now, today, I see that most of you pick 60, answer A. I don't know if you could justify it, but you picked the right answer, and of course I don't know what was the reasoning, but this is the reasoning, and I try to be as thorough as possible, right? Okay, and the major point is to remember that bulbs produced for the US, power of the bulbs calculated assuming that you use 120 volts potential difference, right? Okay, that's the major trick of this problem. Okay, so that's the question which I like, and now RC circuit. Probably I wouldn't be able to finish it, at least I will start. So, what's so special about RC circuit? It's a first circuit where we are going to see current changing in time. because up to this point, all the time, currents were steady. They were constant in time. And it's the first example, the simplest example, when current changes. So how are we going to change current? There will be a capacitor, first empty capacitor, right? And of course we can charge that capacitor. Of course, in order to charge it, we need to have a source of charges, right? Battery. If we connect just directly battery to a capacitor, the process can be too fast, right? And we can damage our capacitor, right? So it's better to slow things down. So it's better to connect them through a resistor. So the current will be reasonable and we will not cook this circuit, right? So, so first we will discuss the case of a charging. So we're going to charge a capacitor. So I will do it in the lecture. And in our recitation classes, we will discuss a discharging case, right? So when the capacitor is full and you will discharge it through a resistor.